and n has to be the partial derivative of f with respect to y, if in fact the level function does exist, right? Does it have to exist though? How are partial derivatives connected? Do you guys remember? If I partial differentiate first with respect to x and then with respect to y, is any different than if I differentiate with respect to y first and then with respect to x? Do partial derivatives commute? Yes, they do, right? Thankfully, unless you're a mathematician and you can come up with a sufficiently malevolent example. But for the applications we're interested in, it's always the case that they commute pretty much, all right? So certainly in the case that m and n are like, smooth functions, they commute for sure. I think all you need is continuous like second differentiability and they commute. But anyway, so what that means is that m and n are not innocent bystanders. They're connected. They're connected through partial differentiation, right? So to speak, this one, let me just get to the point here. We need that partial m, partial y, which is partial squared f, partial y, partial x, right, is equal to partial squared f, partial x, partial y, which is, by the way, partial n, partial x. This is a necessary condition for the equation to be an exact equation. Now, Austin, the integrating factors you were looking for have to do with what we're just about to get to. Like basically, the additional integrating factors stem from, okay, so like, let me just state the theorem we just found, right? So it is m dx plus n dy equals to 0 is exact. Implies that partial m, partial y is equal to partial n, partial x. Now, that, it's a little bit subtle, all right? When we can reverse that, this, in order to, if you want to reverse this, then you need the condition on a simply connected domain. Because the reason that it works in the reverse direction has to do with Green's theorem, and Green's theorem applies on a simply connected domain. I'll show you that another day. Okay, I won't get into that right now. But that's that's pretty much a no-go theorem, right? I look at a differential equation. If it fails this simple condition, it's not an exact equation. So, like for example, if I had something like x squared dx, right, plus y dy, bad example. Let me try again. Plus xy equal to 0. If I had this differential equation in Foppian form, and by the way, guys, you could go back to the regular form by just solving for dy dx if you want, but obviously the Foppian form is the more natural one to look at for this discussion. So is this an exact equation? In other words, is it possible to say that this thing, is this equal to df for some f? I don't think so. So here we have m is equal to x squared. We have n is equal to xy, right? So partial m, partial y is what? You guys are making me do all the work, aren't you? Fine. 0. I guess I get paid for it. Although only 7 of you, so not as much. Here, y. I don't really care, guys. I'm happy to just have 7 people, it's fine. I'll just get an overload next semester, it's no big deal. Anyway, so that's that. And are those equal? Well, no. Those are not equal, right? Unless y is equal to 0. But you can't just make y equal to 0 on the whole thing. I don't know, maybe y equal to 0 is the way you get it out. But I mean, this is not generally true. So, not exact, all right? So, the idea of an integrating factor for an exact equation is something like this, right? What would the idea of an integrating factor for an exact equation be? Something like this. I go from, I take my m dx plus n dy, right? And I multiply that by I, right? And that would give me like im dx plus in dy. And if that's a legit integrating factor for this exact equation, the resulting differential equation would be exact. All right? So maybe this equal to 0 is exact. What would that mean? So maybe I call this thing like m tilde, I call this thing like n tilde or something. What would I need? I would need m tilde, partial m tilde partial y is equal to partial n tilde partial x, right? And so that's where those special integrating factor techniques come from. They come from just imposing this condition on specific cases of an initial m and n. If the original m and n have a particularly special form, you feed it into this condition and you can work something out. That's not in my notes, actually, I don't believe, but it will be in the book that I purchased through the bookstore. Anyway, let's see here. Now, Pfaff's theorem basically says such an I exists. But the rub, of course, is, in general, finding that I is just about as hard as solving the differential equation, so it's not really that comforting unless you can just kind of eyeball it. Can you eyeball it? Can you make this differential equation exact? Let me ask the question in a slightly more focused way. Can you see something we can multiply the example 6 differential equation by so that both the m and the m type terms, like the m tilde and n tilde, let's say, both have the partial derivatives that we need 0?
You just divide by an x.
Exactly. Very good. So if we just put I equals to 1 over x, and that gives us x dx plus y dy equals to 0. This is a very circular example. So sorry. So this is this is the differential of 1/2 x squared plus 1/2 y squared equal to 0. In other words, the solutions are 1/2 x squared plus 1/2 y squared equals to a constant. There you have it. Is what I just wrote in purple and I'm about to bubble. This bubbly thing I should hear. The one in the cloud. Is that the same differential equation as example 6? Now, the integrating factor technique that I've erased, something you might notice about it, the exponential, we're taking the exponential of the integral of something, right? The integral is an integral of a continuous function, or at least a piecewise defined continuous function. So that integral exists, and it's the exponential of something, right? So it's positive. We're not changing the solution set by multiplying. Multiplying by a positive thing. Whenever you multiply an equation by something that's 0, identically 0 someplace, or you divide by 0, you might be losing solutions, right? Or if you square an equation, you might be gaining solutions, right? These are manipulations of equations that you have to worry about. You're changing the solution set. For the ordinary integrating factor technique, because of the structure of the integrating factor, the solution set is not changed, and our solution is general. It's really cool. For these kinds of integrating factors, though, see here, like, it's a good, good call. But you notice that this is going to let us down when x is equal to 0, right? So you can ask the question, is x equals to 0 for all y? Right? In other words, thinking of x as a function of y, which we wouldn't be allowed to in pre-calculus, right? It's a vertical line. It fails the vertical line test in the worst way possible. But it is in fact a function of y. Is that a legit solution here? X equal to 0. Yes. So x identically equal to 0, the graphically vertical line solution. It is a solution to this differential equation, but not this one, not this one. See, x identically equal to 0 leaves you with y dy, which isn't 0 for that solution. So these are in fact different differential equations. This one has the x identically equal to 0 solution, this one does not. So the integrating factor lost something, but that's not a big deal. You just go, okay, when I multiply by the integrating factor, I have to take care to keep track of my extraneous solutions. In this case, the extraneous solution is just x identically 0. So, sorry, if I had done this with something like, if I had done like, you know, xy plus y squared, we would have lost the y equals 0 solution, and it would have been less weird to you, what I'm saying. But the same comment exists for that better example that I didn't think of. Those are your 3 methods. Do you feel educated? Yes?
So what you would want us to give you for example 6 was what you have boxed for it, and then also or x equals 0, something like that?
Oh, right, yes, the total answer here is this, or x identically equal to 0. I know. The identically 0 is popular notation in these kinds of conversations. Now, let's see here. I'll tell you where we are, where we're going. So basically we're in chapter, I have said to you a few words of my chapter 1, and you know, chapter 1 should be just like, you just glance over it, you get a sense of it, you read it quickly, come back to that later at the end of the course to really appreciate it, all right? I have a long laundry list of popular differential equations in physics in my chapter 1, so if that excites you, look at it. If it doesn't, skip it. Won't offend me. Let's see here. And then like section 2.1 is separation of variables. That's kind of self-explanatory. Section 2.2, integrating factor method. Oh man, I guess I cut these notes down. I used to have like 15 examples. But I have links to like my old Calc 2 notes, which have like 20 integrating factor examples. I have oodles of solutions online. If you're ever missing, if you ever need an additional solution, just email me. Exact equations is section 2.3. We've hit that pretty hard today. I have not explained the connection to conservative vector fields and exact equations just yet. I'll try to lead with that next time. And I have a little bit on, this is section 2.3.2 in my notes, is roughly speaking what we're trying to do, is talking about right now. Example 2.3.12 on page 29 is kind of a more systematic version of the guess you just made. But instead of like a more sort of fun, generic integrating factor, you might try with something like this. These make for kind of nice homework problems. Choose A and B that makes it work. You know, you're like, well, how do you know A and B will make it work? Well, it's a problem, but sorry, some of these things are sort of artificial. And let's see here. And that brings us to substitutions, which hopefully I'll spend a good bit of next time on substitutions and perhaps some of the, maybe, I think I may talk about some of the theory of the, like the basic, there's a couple of theorems that sort of are comforting and tell us that, hey, we can always solve these given certain conditions and there exists a unique solution and some things like that. So I should probably share those things with you. Don't worry, I'm not expecting you to prove a theorem or anything. It's not like that. But we do need to know so that, we should be aware of it so that we know what we're doing is going to work, right? Anyway, I hope you understood something. If you didn't, I'm sorry, but you need to ask questions if you're not understanding. Certainly there's time for your question in here, and if you're not understanding, there's a pretty good chance that 2 or 3 people sitting around you also don't understand. And even if they do, it's still good for them. So, do interrupt me, I don't mind. Okay? Don't make me put a sticker on my laptop to remind you to ask me. It's too late, I already bought the sticker. Okay, more on that next time. Thanks, guys. You can, yeah, thank you.